esteemed privilege now to introduce to our next speaker. He is Dr. P.C. Pant. He is a well-known renowned name in the field of solar energy. He needs no introduction. Still, I am giving a brief introduction of Dr. P.C. Pant. He is a superannuated ex-scientist director from Ministry of New and Renewable Energy. He holds a master's degree in physics and done PhD in solar energy. And he has experience of vast research experience. He has prepared and implemented of integrated rural energy plan for 4 blocks of Uttar Pradesh for a period of 14 years from 1984 to 1988. Planning, system design, installation, and managing 4 community plants, solar water heater capacities of 100 liters per day to 42,000 liters, SPV power plants of 900 per peak from 20 watt kilowatt peak, both off-grid and on-grid system, windmills, SPV pumping systems, night soil-based biogas plants, monitoring and evaluation of renewable energy projects in various states for a period of various decades. He is doing that. Now his international cooperation of negotiating team with the World Bank. He has published various research articles in Scopus Index Digest and various other research entities. He is a very huge name in the field of solar energy, solar thermal, biogas, and hydro. So I request Dr. P.C. Pant to kindly join us and share his thoughts with the participants. It will be a great opportunity for the participants to hear his views and interact with the participants. Now I am allowing Dr. P.C. Pant to make a host, sir. Very warm welcome to you, sir. I am making you the host, sir, so that you can share your slide.
Hello. Hello.
Hello, sir. You are the host now. You can. Hello, sir.
Hello.
You are audible, sir.
Okay. Okay.
Yes, sir. Audible. You are the host.
Yeah, I'm trying to upload actually. I share that.
No problem.
Whether my screen is visible?
Yes, sir. It is trying to view your screen. Sir. You are the host now. Your screen is visible.
No. Could you see my presentation? My screen?
No, sir. No, sir. No, sir. It is not visible yet.
Just hold on. Let me destroy it. I think I have to rejoin actually. It appears to be because.
Okay, sir. You rejoin. Sir, you rejoin, sir. We will wait for you, sir. It's a pleasure to have you. You rejoin.
Share it because now is it visible? Hello.
No, sir. Yes, yet it is not visible. Yes, now it is visible, sir. You can.
Now is it clear?
Yes, sir. It is clear. You can go ahead, sir.
Okay. Okay. So good afternoon. It's really an honor and privilege to be associated with the prestigious University of Lucknow, the Department of Physics. and particularly with the Center of Excellence on Renewable Energy. To some extent, my association with this center started way back in 2009, actually, when a new HRD policy was developed by me. Hello. In the HRD policy, actually, renewable energy was incorporated, and that was incorporated in University of Lucknow. A small grant from the ministry was also given to them, and some fellowships were also given. Of course, the fellowship program always had ups and downs in the ministry. But whatever it is, now I retired last year, but still keeping myself engaged with some of the activities of in the field of renewable energy as a professional. And I'm the member of Board of Studies of NIT Jalandhar and Vishwakarma Skill University Gurgaon, as also I'm the member of the expert panel on energy storage for their FLCT project, which is basically on innovation. So that's what I am, and I'm being told to speak something about solar thermal systems. So yeah, want to raise some query or anything, they can raise in between. It depends upon them, because in this virtual environment, actually, you don't get that type of feeling actually, which you used to get in a classroom environment. So anyway, I'm going ahead. So friends, as you all know that practically, if you look at the renewable energy aspect, the renewable energy movement practically started in 1973, when suddenly the OPEC countries, they had just actually increased the oil prices by 4 times, and the economy of all the countries got disturbed because the kitty available for them for meeting the fuel import got suddenly increased by 4 times, and that's why the entire economy of every country got disturbed. And then the people thought that can we become energy independent? And that process actually, this renewable energy at that time, it was not renewable. We used to tell it as a non-conventional energy sources of energy. So shifted to some energy sources of energy. But today, the non-conventional energy sources of energy has been renamed as a renewable energy, because and it has become mostly the mainframe energy source of the country. But unfortunately, what has happened during all these processes, that energy, which is a broader term, is being confused with the electricity. Actually, electricity as such is not an energy. It's basically a mean of transporting energy from one place to another place. And that's why we use the word current. So long as the current is there, the flow will be there. And so you are producing somewhere and then transmitting it to some other place, and then using it for various applications. So the electricity became the focus point of entire energy scenario internationally. But if you look at the total share of electricity in the entire energy basket, you would find that only total energy consumption, which includes, of course, electrical energy, but as well as the other, like the transport sector or process heat sort of thing. It's the total contribution of the electricity is 21%. The rest is, of course, a major portion is on transport side. And then the process heat, which is something around 45 to 50% of the total energy basket. So that's what is the overall energy scenario. Of course, the way the developments are going, it is expected that in next 20 years, the the contribution of the electricity would be somewhere around 45 to 50%. But still another 50% will be to process it and those type of things. So that is the total basically scenario. And when all these scenarios were being discussed and try to find means of utilizing the non-conventional, then the shifted to means what could be the, so ultimately it's thought that primarily if you look at, so these are the 4-5 primarily available in which that serves their source of energy. And in addition to that, of course, the motion and the gravitational potential of the moon and earth, that is also a source of energy in a sense that get tides to it, and that tides you can store water and use that energy for generation of electricity. So this is it's dependent on sun. Then of course the geothermal energy, which is basically from the chemical reaction and the radioactive decay which is taking place inside the earth. So and which creates some heat, and that heat is basically the somewhere if the hot water is enveloped some craters of, you can use the energy. So that's basically the geothermal energy. So that again, not basically the source is not sun. Basically, it's basically the chemical and the radioactive decay. Then of course reactions you all know, and ultimately this nuclear reaction is practically the source of all the energy which is coming in from sun. So some nuclear reactions which are in place or due to radioactive activities and all those. So that is another energy source. And of course, the chemical reactions from the mineral sources, you know, there are a number of exothermic reactions due to in different chemical reactions can we use those exothermic reactions to generate some energy and use it for various applications. So primarily these are energy sources. Practically the sun, the motion of and gravitational potential from moon and earth and the geothermal energy source. They are thermal as a renewable energy, but practically it is not a renewable energy because again it is a stored energy. It has its every geothermal well has its own life. And then you have to search for some another geothermal. But there are places like the Iceland, Philippines. There are a lot of geothermal energy. Means the geothermal energy is being used for various applications, including electricity generation. They have huge resource available. As far as we are concerned, the country not much of a thermal resource is available. Whatever little is available somewhere in some places, and that is being used either for purposes or now in Pugali we were looking to have the economics or the financial viability of that deterred us to go ahead with geothermal power plant. So that is what it is. But ultimately, the fossil fuels are also generated from sun is basically the main source of energy. And practically, if you look at the renewable energy is practically obtained from the continuing and repetitive current of energy. So whatever we are getting solar energy, when we talk about solar energy, it's coming in the form of heat. It's a current energy. In a sense, it is an income. To us, whether we use that income or we do not use that, ultimately comes in the form of only why the so these are the when we used as energy source. You have to have human interaction to generate extract energy out of it. Like if you take some coal in your hand, but if you go for the practically is so practically, if you look at, see, ultimately the renewable energy, it is coming from the environment, and ultimately it is going to the environment. So environment is acting as a source, and environment is also acting as a sink. And it is directly coming from energy itself, like the solar radiations. So they are coming from the sun in the form of, you can say, heat or light, the visible portion, and ultimately part of that is being absorbed by the earth, and ultimately the earth or the atmosphere is acting as sink. All whatever is not being used that goes in the. But as we are accustomed to various applications now, means if we look at our lifestyle, we do not want that to take a lot of time, and that's why whatever incoming radiations are coming, we have to convert it into a useful form of energy, and for that you require a device, and from that device actually you use whatever the application you can do through that. Maybe those radiations can be used in a photovoltaic device to collect, and then the electricity can be used as applications, maybe lighting for lighting purposes or heating purposes, or running the ACs or fans, or even in industry and all that. Or you can collect it, the heat, and then use it for maybe heating water, or generating steam, or space heating, or even for refrigeration and cooling purposes. So different thing, but you require a device in that case. But if the device, even the radiation or the solar energy is available to you for various applications, like if you want to dry your clothes, if you want to season the wood, all those could be done directly by the solar radiation. You simply have to sun, and you find that we can do a lot of applications only without any device there. But as far as the finite energy sources are concerned, like the fossil fuels sort of thing, you particularly require a device. Without device, you cannot use means that source of energy. If the diesel is there, then you require an internal combustion engine to burn that fuel inside, and then run your engine from that. If it is a coal, then you require a furnace where you have to burn that, and then generate heat out of it, and then use that heat for whatever it is. So ultimately, in these two, both the things, ultimately whatever portion is being used, that is being used, but which is not being used, that is going as waste and going to the environment. Ultimately, the efficiency factor which comes into picture is how efficient the device is. But the sink part has not to do the work. So I have to optimize the process of conversion of that particular energy in another use form for the, and the wastage of energy should not be there. And that's why the energy efficiency factor has come into picture. So ultimately, if we look at the energy planning, basically, there are two aspects which are very important. One aspect is you should find the source, and from that source, you have to develop a device which should be energy efficient. So in the planning process, basically to get the source and then find the application, and the application in such a way that it becomes efficient. So both the things are going hand in hand, means using more and more renewable energy in a very efficient way. That's what is the total planning process is going. Now, if we look at, means if you look at the planning process, so ultimately you have to see that how much energy resource, whatever is available, that is available with to us. And the second and the most important aspect is purpose for which the harvest energy is to be used. The purpose is very important. Means whether you have to run a locomotive, whether you have to run a bus, whether you have to heat water, whether you have to directly convert it to the electricity, and then that use that electricity for any other purpose. So ultimately, until unless you are not clear that for what purpose you are doing that, you cannot do just with basically the efficiency aspect of that. And particularly that will have an impact on the cost of the energy which you will be producing. And that price of energy ultimately, means the energy generated, and if it goes for application, if it is not being done efficiently and potentially unviable, then even I will not use it. And that happened actually some 90 early 2000, when the cost of the electricity generated from solar devices were so high that nobody went for that. Of course, the lot of research and of course the economy of scale had also played its role, and ultimately the cost had come down, and now the people have started adopting that. So that's what is the overall scenario. Look at the means whatever the total source of in the earth atmosphere, we get the solar radiation, so and ultimately we get around 1 terawatt, which is and that we again use for different applications. Part of that is being absorbed or the plants with photosynthesis, and through this process we get our food, or the plant also get our food, and then we are also using that those plants for even for energy producing, like we have now been working on the biofuel or the gasification and all those type of applications. So the basic source is coming from sun. And then another thing is the kinetic energy, means whatever solar rays are absorbed. So in a particular place, if the temperature difference is there, and wind start blowing from one place to another place, ultimately the kind of blowing of the wind, or even in sea, the waves are basically, and we use energy, whatever is there, because of it's a flow. If the flow is there, that energy part is there, you can use it for various purposes. Then the latent heat or the potential, like in a sense, It's basically flow of water sort of thing. And the hydro potential, you can say, can be used through this. And ultimately, the sensible heat means that wherever the solar radiations are coming, you use those solar radiation either for generating electricity or use that heating part for various applications. So ultimately, if we look at all these things, and then we have to understand that how the solar radiations are coming to our atmosphere. Ultimately, if you look at the solar spectrum, this is practically the solar spectrum what we have been getting. It has primarily three components, which is the ultraviolet component, ultraviolet, which is below violet, and then the visual part, solar it includes somewhere around 6-7% of this. And part of it is basically the infrared part, which we feel practically. We don't even feel. Like you might have observed that usually use a term called red hot. Means when you heat maybe an iron rod or something, so you feel that energy. It's the radiation actually through which uh, uh, I think, is there any problem? Am I audible or I'm getting some kinks here. Hello, no reaction is coming from other side?
Your voice is breaking, sir.
Oh, okay, I'll try now to keep my mic here. Perhaps, yeah.
Now
So,
and then, sir. It's not always.
okay, okay. That may be the because of maybe internet connectivity and all that. Though the Wi-Fi is good in my place, but still sometimes it happens. Okay. Anyway, so around 49% is basically the infrared part, which we feel basically, but we don't see it. And then as we increase the temperature, means basically the winds displacement process basically. Okay. To increase the temperature, the wavelength to the lower wavelength side. So we do the visible part. So first thing is red, then yellow, violet, that sort of thing. So that is what practically we cure. That is the visible part, what we see, which is something around 47-48%. And the rest 3-4% practically the ultraviolet part. But the most of the ultraviolet part is being by the atom. So, but if we look at radiation coming, so solar distance between Earth and Sun very large, basically 149.5 kilometer, and radius wise also the Sun is quite large, is very small. So practically here, if you be this thing, it appears here, it's not like this. It's basically tending in only 30, even less than 1 degree. But it and subtracted. So practically, if we see, have a very small, let me put it this way. If I put a small angle like this, is it visible? If you see a big angle, I do not know whether it is visible or not. And if you far off, then this portion don't catch up the parallel each other. And that's why whatever radiation is coming to us, we say parallel radiation or the beam radiation. And the second part of the radiation which is coming is basically the diffuse radiation, which is yeah, it is like this. If you look, this is the solar radiation. So part of the solar radiation which is coming, it is from the atmosphere, it is reflected back. And the direct radiation, which are the sun ray, which is straight back coming to Earth without any scattering or deviation in its route, that we say the direct radiation. And part of the radiation which is being scattered through reflection or whatever it is, there are dust particles, there are water vapors, the clouds are also there. So from that means the radiations are coming after having a lot of reject Earth sort of thing and ultimately coming to Earth. That we say the diffuse radiation. And the sum of that two is basically the global radiation. That's what it is. And practically outside the atmosphere, there is no atmosphere, we get something around 1367 watt per meter square, which we say the solar constant. As it comes inside the Earth, because we have an atmosphere which comprises of carbon dioxide, ozone layer, water vapors, N2, O2, sulfur, or whatever it is, methane, all those things. It makes an envelope basically in that Earth atmosphere. And because of that envelope, particularly because of the ozone layer, most of the UV part is absorbed there. So we get a very small UV part, which is not very good for the our skin and all that, because it's a low wavelength but high energy. And that's why sometimes when the lot of UV comes for some reason, because as the scattering takes place, basically the lower wavelength that gets affected, and the lower wavelength has more energy, and then in your skin, because it gets burnt basically. So that's why but ultimately the solar system which is falling inside the atmosphere, that gets attenuation. And normally as a standard we say that 1000 watt per meter square or 1 kilowatt per meter square, that is the rate. At a particular point we get that much. It may be less or maybe a bit higher, whatever it is. So ultimately we look at the solar radiation means the spectrum. The spectrum is something like this, means the ultraviolet part, visible part, and the infrared part. Outside the atmosphere, we get that type of radiation, means it's almost smooth. But as it enters inside the atmosphere, we get a lot of absorption band, some because of the water vapor, some because of the oxygen, some because of the nitrogen or whatever it is. And ultimately, this is a type of spectrum we get, which we say the AM 1.5, which is basically the air mass. Ultimately, what happens basically when the sun actually travels from morning till evening, the actual distance means a sun ray travels basically from within the atmosphere basically. That distance changes. When it is overhead, then we say it is on in the zenith. But if it is parallel, means just in the morning, it is just coming up. The sun is coming from the horizon to the upward side. The distance covered is more. And that's why when the distance covered is more, then the absorption will take place more, and the atmosphere means the spectrum will change. So for standard purpose, we say the spectrum means when the angle is somewhere around 49 degree. That is the angle. At that time, what will be the spectrum? That is called the AM 1.5. And this is practically being used for the standard in switch in photovoltaic. So that's what the ultimate look at the solar whatever solar radiations are coming. If this is the solar radiations 342 watt per meter square, if it is coming like this, then part of that will be reflected directly either from the earth or from the atmosphere, and it goes back. Then part of that will be absorbed by the earth's surface, and it will again going back, which will again be trapped by the greenhouse or the vapor or the gaseous layer, which may and practically what now that is and that was such a way that this atmosphere layer outside the atmosphere doesn't thicker, so that our temperature should not rise beyond maybe 1.5 degree Celsius of average atmospheric temperature. So that's what it is. Ultimately, the it's was there. So in a sense, this is what already explained all you. So in a typical cloudy day, we get mainly the diffuse radiation. But when there is a clear sunshine, then we get mainly direct radiation. Probably measure the radiation in maybe September, October period, or there in February, March, April sort of thing. You would get a radiation level of something around 800 or 900 watt per meter square, and most of that direct radiation. But if you get there may be in a typical cloudy day, and then the total incoming radiation, which will be Earth will be some around 300 or 400 watt square, and then will be the scattered radiation or the diffuse radiation. So our aim actually now in the solar application, we have to use actually both and the diffuse radiation both such that we can collect that heat, and that's why in the thermal application we use the word collector, while in the photovoltaic application it is direct electricity means radiation into electricity. So there the spectrum portion of the solar radiation, that while in the thermal application it's basically the radiation which is falling. Ultimately our aim is to absorb that entire radiation. That's basically then generate the heat out of it. We use the heat portion of it and use that heat in solar photovoltaic. Solar radiation availability. You might have heard basically of International Solar Alliance. When the International Solar Alliance was conceived way back in 2015, and ultimately the Paris between the Tropic of Cancer and the Tropic of Capricorn, means somewhere this portion and this portion. Most of the solar radiation means it is very good. The solar intensity is very good. So if you look at this polar side on the extreme north or extreme south, if you go, then the solar radiation level means annually, if we look at it is even hardly 800 to 1100 kilowatt hour per square meter. That is which you get in a year. Okay, but go a bit ahead, then you'll see that it's 1100 to 1400 a year, like in this portion, then bit more. But as far as we are concerned, we are somewhere here, which is 1700 to 1900 or even 1900 to 22,000. So that's what is our level. And ultimately, most solar radiation that is, and that's why we thought these all the 122 all within two come together and make alliance so that the optimal utilization of the solar energy we can do. Now, of course, with the success of the solar alliance, almost all the countries are becoming part of this alliance. But that is the one very great achievement of India of making an alliance and being the leader of it. And so important of solar energy. And is the solar energy. So how the solar energy is coming? Actually, if we look at the utilization of the solar energy, so there is one, the direct method. The indirect method is practically which is the hydropower you should, or the wind is blowing only because of the solar radiation only, because it's the temperature difference between the two places which allows the wind to blow from one place to another place. And then the biomass, of course, the photosynthesis process, huge, you get the biomass, the wave energy, again similar like the wind. And the ocean temperature difference means there is a temperature difference on the upper layer of the ocean, and then some maybe 4 meter, 5 meter, 6 meter below. So there will be the temperature difference, and that gradient can be used for generation of electricity, or which we say ocean energy conversion system, basically. And to some extent, that is also being used. That principle is also being used in the solar, wherein we make different layers of salty waters. On the top, it is pure water, and then a bit salty water. Then the layer concentration will be more. So as the concentration will be more, that will be heavier, and so it will be lower. So when the temperature the top, and part of that it's going down, it's being used for generation of electricity, all that. So that's basically the indirect method. The direct method, of course, there are two methods. One is basically, as I mentioned, that you use the heat portion of solar radiation. Whatever solar radiation is coming in the form of energy, as I mentioned, is coming in the form of energy. So that energy is that from that heat you do number of applications, whatever you feel like. And the photovoltaic is practically direct conversion of electricity, solar radiation into electricity, and electricity is produced, then electricity for whatever you want to use it. So that's what it is. Now, if we look at solar thermal, which is basically the irrigation of uh, 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 classified based on its application. So you can have a low pressure application, which is practically for all those, but you don't require the hot water. You require a water of maybe around 30 degree or 25 degree or 15 degree even. Sometimes it becomes very, say, the atmospheric temperature is 4 degree, you get even 15, 20 degree hot water. You will feel it's warm. Like you might have seen in the hand pumps. Bore water. Most of the time we say that the borewell water is in winter and it's cold during summer, and we feel it. Okay, and so we can direct water coming from even during winter. It's not that water increased. It's not the water temperature remains atmospheric. So that water means 4 degree or 6 degree warm water, we feel like it's hot enough for. So that type of, so in the deep water, because water is too cold, so a swimmer may get some cold stroke or whatever it is. So to make the water comfortable, we can use the solar device. The local actually make which is compatible and the swimmer can. Similarly, the desalination, it's really the evaporation process. It's an evaporation. What we say. One is the boiling and another is the vaporization. The water vapors are generated even at a very low temperature, it basically being used. And that heat is, so you don't require very high. So that is you the water. Other application could be like the listening of one way directly keep we say the input which you immediately hello. Yeah, my voice tracking that message I'm getting. It's so if say a wood log is there, which is from a that have moisture, and if you use that moisturized water application, ultimately that will get deformed and would not good quality. So you season that. So one way of seasoning it and dry. Actually, it's the vapor, water vapor. So that's the difference between vaporization. The vapors, it's a continuous process. But in the atmospheric temperature, the vaporization will take place. So you don't require large heat vaporization. So that vaporization process is being used in the desalination of water. So if the solar is so basically the collection heat is generated and it gets vaporized, and then I'll do that later. this is the medium temperature sort of thing, wherein you require a temperature or something around 60 degrees, 20 degree, 80 degree or 100 degree sort of thing, which is basically mixed in the cold water and then can be used for various applications. Or maybe directly low grade, low steam generation sort of applications. So that's the medium temperature. In this temperature, practically the device which you use is maybe the solar hot water system or your solar cooker, that type of application basically comes within this medium temperature. And then the high application, maybe of the sort of thing. And ultimately you transfer that heat into a fluid and then transfer it into a, put it in a boiler and generate steam and then ultimately generate the electricity out of it. So these are the three practical applications based on which the solar thermal applications are classified. And accordingly, the device is being made. Practically, if we look at in any solar thermal system, it will have one heat collector. And that's why I'm using a collector here, but you have to collect the heat. Then there should be a heat transfer mechanism wherein the collected heat is transferred to a working fluid or maybe the air itself. And then whatever heat you have transferred actually from that collector to that working system, that should be somewhere. You require a storage tank. It may be a simple insulated hot water tank or maybe boiler sort of thing. And ultimately, yes, of course, if you have to make the system more sophisticated, then you can have a regulator system also wherein you can use means you can maintain the temperature or run whatever it is sort of thing. So a regulator system may also become the part of it. So whether it is a active system or the passive system, active system in a sense where you have the regulation mechanism, passive system is it is working of its own. So that type of thing. So ultimately what is whole idea is means we are getting the solar radiation and that solar radiation needs to be used for generating heat and that heat needs to be trapped or collected somewhere. So that's what is the whole principle in which the solar thermal system that basically we look at in a typical solar thermal here it's basically the schematic design is there. So you have a solar collector. If it is an active system, then you may require a pump. But if it is a passive system, then because of the thermosiphon also, you get the maybe flow there. Ultimately, this is how the thing works. So practically, in a collector, what is the collector? Collector, it absorbs the solar radiation and the solar means the sunlight or the not use the word light, it's the radiation, okay, which is converted into heat and that will be trapped or the collected and then it is transported the heat to a heat exchanger via pump or directly at maybe thermosiphon method. And that heat exchanger transfers into different another fluid and ultimately you use it. So practically in a solar collector, which is the in a sense the heart of the every solar thermal system that transform the solar radiant energy into heat and can be used for different purposes, a sort of repetition practically. Now to understand actually how this whole process takes place, we have to know that how the heat transfer takes place. There are only three methods, you know. the heat transfer process. One is the conduction, then the convection, and the third is the radiation. So in a sense, if you want to understand this thing, it is like if I have a maybe, fruit available, we have to distribute in say 10 student or 50 student or 20 student, whatever it is. So there could be three methods. One method is because I have the fruit basket. So what I can do is I give to the nearest available student and will tell him you pass it on to his neighboring student. So this way the fruit will go up to the last point. So in a sense, the source, I am the source of energy, and the conduction takes place, it's basically the molecular or the atomic process. So the heat is absorbed by first atom, then or the molecule, whatever you say, it transfers to the another nearby molecule, then it transfers to another, and then ultimately it goes to the last process. That's what it is, basically the conduction process. The convection process is like that I give the entire thing to the first student, and you just open this basket, you take your own portion and then pass it on. It gets lighter at something at the and it lighter, then it again comes to the. So that's how it is. So in convection process, that's what it is. Conduction, the radiation is absorbed here, and then the convection current is generated. And therefore radiation, it is like that. I'm just throwing the that throw to individual so everybody get no medium for radiation. It's directly coming. So the radiation is coming like this, and then when it hits the metal, so it gets heated up, and because of this heating up, the air gets heated up, and then the convection current is generated, and ultimately, if I trap all this thing, then the whatever is left, that will again go in the atmosphere. So that's what is the process, basically the heat transfer process. So what my aim is in a collector to collect as much as possible. So if I have to collect a thing, so the first thing which is required is the conductor. Means where the solar radiation falls on a metallic surface, what will happen? It will have good absorption. It will absorb it, but it is a good conductor of heat, so that the heat is usually distributed in the radius. I take a good conductor material. It can be iron, it can be copper, it can be aluminium, whatever it is. And then the solar radiation is falling on that collector. Once the solar radiation falls on the collector, what will happen? It will absorb. Now the second thing what I need to do, whatever radiation is falling on this collector, I need to absorb it maximum. So it should have good absorptivity. And when I have to make it good absorber, means the higher the visible portion, which has the higher energy content, that needs to be absorbed. The UV and the visible portion, that should be absorbed. So if I make it in such a way, like if I coat it with, say, a black paint, what will happen? The black because it has absorbed, it absorbs the rays. It has absorbed, and sheet. And once it is rise, the temperature has risen. What it will start radiating. So the heat the loss takes place from if you insulate this collector plate, whatever it is, which is from the bottom of from conduction place, if you keep it or surface, the another surface means it will be transmitted to that particular molecule. So if you use an insulator, a thermal insulator, make a layer of thermal insulator at the bottom and at the side of that plate, what will happen? It will reduce the conductive losses. It won't miss, it will reduce. You cannot do away with that, but it will reduce. Okay, significantly it will reduce the conductive loss. So what you do, box sort of in which the collector plate is kept, and at the bottom and the side of that box, you use the insulator so that the conductive losses are minimized. That is what is done here. You see, this is the and then now and once it's heated, water it will start radiating. So there will be two types of loss take place. One is which is across surface, the color surface that is heated up, and the convection will generate. Means the through convection the heat loss will take place. So we have to reduce the convection losses, and then we also have to, because it is now heated up, so the higher wavelength radiation will be, which is the heat radiation, that will go out. So the losses will take place from two methods. One is the convection, and other is because of the radiation. The higher wavelength will go out. So if I make an arrangement in such a way that if I put a transparent glass sheet here, glass is insulator. Practically, it's a not a good thermal conductor. So the top and the bottom. Okay, the flux current, the air which will get heated up will touch here. It will get cooler and then again will come. So the convection current will be generated inside this box if I make a gap in between the two. The second is the glass has a characteristic that it is visible wavelength and open to the IR practically, which is the heat radiation. So it what the go out. So if this trapped the heat inside this box, what I have created. Now my job is that I have to transfer whatever heat I have collected here, and that's why I use the word collector here. Whatever heat I have collected here, I need to transfer it to a working fluid. And how to transfer it to working fluid? So what I do is I take a, what I said, a header sort of thing in both the sides. I put a pipe, tube sort of thing, and from that tube, I start putting the pins. Means this header will have larger diameter and this pins will have a very small diameter. So ultimately, two effects will take place. One is practically, and then I start flowing the cold water from the bottom. So the moment the cold water goes here, it comes in contact with this collector. The heat transfer will take place. And because of the heat transfer, what will happen? The water gets heated up. The moment the water gets heated up, it will become lighter and it will start rising, which we say the thermosiphon process. So through these pins, which will have a bit of capillary effect also, as well as because of the thermosiphon method, the water will rise and come to the header. From header, I will take the hot water. So that's how actually I make a collector, which I say a flat plate collector. We look at only one radiation. Like it is like this. If I put it in such a way that the maximum, the solar radiation falling on it on the normal range inside, and from the bottom I will put the hot water, and from the top it will come down. Yeah, it is something like this. Okay. Now what is happening here is only one radiation. Yeah. Now look at this. If it is a flat plate collector, the design I have explained so far is practically a flat plate collector. So in the flat plate collector, you see that one ray which is coming from here will touch a one particular point. That clear? The solar radiation at particular point, only one ray is coming. So in a sense, in a technical term, I say that only one sun is intercepting a particular point. Of course, the diffuse radiation will also come and play its own role. But ultimately, it's the direct radiation which are falling on the flat plate. So at a particular point, only one ray. This ray is coming and it is coming to this point. So this collector has, for whatever design or whatever means how best insulation and all energy trapping mechanism I use here, I will not be able to generate a temperature of maybe more than 130, 140 degrees Celsius at most. Okay, and then I am transferring the working fluid, and heat transfer will have its own efficiency. Ultimately, get a temperature of 60, 70 degrees Celsius. So, which is basically in the mid, and I can say that if I work this type of temperature range, then I'll use a flat plate collector. But now if I have to increase the temperature just hold on. Now increase inside this collector surface. What I need to do is I need to increase the radiation level. Now the radiation is coming in the form of direct radiation. So in this solar, this is a box type solar cooker. Just let me take some water. This one. Now look at this is a box type solar cooker. Okay. And I think many of you might have seen it or even may have used it. In fact, practically I have used the solar box type solar cooker for about 20 years. Of course, now I don't have at the moment. But in 1985, I bought the first solar cooker, which I used for 25 years. A bit of repairs also, but today, unfortunately, I do not have it because of some reason. Okay, now look at this. What we have done, the same thing what I had explained. I have a box, okay. In this box, which is insulated, the sides are insulated. Inside is the collector plate. This black one, whatever you are seeing, it is a collector plate. If I energy the radiation, it is coming that to a point. At this particular only one ray, okay. The second ray is falling at this point. The third ray is falling at this point. The fourth ray is falling at this point. So at particular point, only one ray is falling. Now what I have done is, I have now put a mirror, a cover of it in such a way that a mirror is there. Now what is happening? Whatever radiation is coming here, I am orienting this mirror in such a way that the solar ray is falling on this mirror and then getting reflected and ultimately going inside this box. So at a particular point, in place of one sun or one ray, you are getting two rays. So in a technical term, I use the word two suns. I am using two sun here. What I have done is, I have directed part of the solar radiation, which otherwise would have gone outside of this box. I have made a device in such a way that that particular ray is also coming inside this. Okay. So what will happen, in place of getting whatever temperature because of one ray, now I am getting two rays at that point, means my temperature will get, I'm getting more energy at that point, means my temperature will rise more. That's what is basically a principle we use in the concentrator. Of course, it's not directly a concentrator, but to understand that I have to some extent given now from 1 to 2. So the temperature is increasing. Now the temperature is increasing. So the convection current will generate inside this. And I have put a glass cover here. Okay. I have put a glass cover here, this type of glass cover. And even to make it more effective, I have put the two glass cover with a gap, air gap in between. Okay. So that because the air is the bad conductor of heat. So there will be large means temperature difference, large significant temperature difference from the top layer and the bottom layer. So entire thing, it will get circulated actually like this. Means the heat radius convection current is going there, and then it is touching this glass. The inner temperature is less, the higher temperature is more, and then it gets cooler and then again coming down. So it will be a sort of convection current and ultimately it will get heated up. And that's what is the greenhouse effect. So in a solar collector, in a flat plate collector, practically what I do, I create a greenhouse so that the entire heat is trapped inside that chamber itself. And if I put maybe anything to cook there, what will happen? Ultimately, in due course of the time, the food will be cooked and release it as required. So that's how a flat plate collector or a solar water heater, or solar cooker, or even in a desalination system, what happens? In the desalination system, nothing like this. It is again like a flat surface. We put some water and then make a sliding surface like this. So what happens? It gets evaporated, water gets evaporated on the top of the glazing is there. From that glazing, again now water gets condensed and it is directed to a bottom level, and from there that's how solar distillation process takes place, and I get it distilled water. So these are the low grade type of solar application. Now if I improve the efficiency of it. Now one is basically the collector. I have to improve the efficiency. So one simple way is, in place of normal black coating, I use the selective coating, like the black chrome type of, which have very good absorptivity at the lower wavelength and less emissivity. So more and more heat is absorbed, and then the radiation level is less. So my temperature gets more heated. That is one way. The second way is, again, as I mentioned, that because of the convection also, the heat is means the heat loss takes place. So I have to avoid that convection. That I somehow make a device in such a way that whatever air is inside this box, if I do away with this air, means if I suck this air inside and create a vacuum inside that, the convection losses which is taking place, I can reduce. And that's what being done in the evacuated tube collector. If you look at this evacuated tube collector, this is the evacuated tube collector. It is a tube. Inside that, if you look at, there is a rod sort of thing, or sometimes it happens it's basically a double wall glass sort of thing, and inside the surface is getting coated with black color, or you can say black chrome or whatever selective coating. So the heat is trapped there itself in the black surface, and between the two layer of glass, or inside that entire tube, I create a vacuum. I suck out the entire air. So what will happen? Once I had sucked out, is there won't be any convection current. So whatever convection losses were supposed to be there in a flat plate can be reduced by way of creating a vacuum inside the tube. And then to make it more efficient, now because the solar radiation is falling on this tube, so this is one way of falling on this roof. But now the part of the radiation is going here. The solar radiation is coming from this, I think if you could see the cursor, then the solar radiation is coming like this. So part of the radiation are going inside this tube and then collected, and part of the radiation is going straight. If I make a parabolic trough here, what will happen? This this ray will fall here and again will go there. This ray will fall here, again will go there. This way ray will fall here, again will go there. So what will happen? A multiple at a particular this tube, which I say an absorber tube, again it's absorber or heat collector. So in this tube, at one particular point, you get not one ray, but multiple rays. As the number of rays are increasing, means more energy is being incident on that tube, means more absorption will take place. More absorption will take place means the temperature will rise. Now I have evacuated it, so no convection current is taking place. It's basically a glass wall, which is allowing the lower wavelength to go inside, but it is opaque to the higher wavelength, which is typically the infrared radiation or heat radiation. The entire heat is getting trapped inside it. So the temperature inside is goes as high, maybe something around 200 degrees Celsius also. So that type of even 300 degrees Celsius also. So ultimately I can get more heat, and if I flow water from here, naturally the temperature I can get a better efficiency in the evacuated tube collector. So this is one way is if I do not use this parabolic trough sort of thing at the bottom of or at the side of the tube, then it will be a simple tubular. And if I put a sort of reflector also, which is a parabolic trough sort of thing, then I'll say it a hybrid sort of tube, which is practically being used for not only, of course, in the water heating is one aspect, but another is basically for generation of means in the solar power plant where you require temperature. Practically, what in place of heat transfer mechanism, in place of water, what you flow is not water, but it's sort of thermi oil. Because the oil has water, what will happen? After 100 degree, it will get boiled up, it will pressurize, and maybe the tube may get damaged or whatever. So in place of that, if you put an oil, thermal oil will go at around 390 or 400 degrees Celsius. And then if you transfer that, you collect that oil to a heat exchanger, and then outside the heat exchanger, you in X, so the pressure will be generated. So you get the pressurized steam, which we call and the way the turbine is run, then the voltage means the electricity could be generated, or even that heat can be used in chiller or even in air conditioning and all those applications. So now actually practically the method in which you increase the temperature through this means like this. This is a typical evacuated collector, unglazed type of collector, which is practically either used for room heating or space heating type of, or used in swimming pools to get a usable temperature in the swimming pool. The different myth, but basic principles, all that is somehow you have to create either a greenhouse, if the convection thing is there, then a greenhouse sort of thing, or you have to reduce the losses by way of avoiding the convection loss and the radiation loss. So that is the basic various applications. Now I have mentioned there's no pump which we use. It's basically because of the water gets heated up and so it becomes lighter and then it makes a current. But if it is a large system, then maybe the this thermosiphon current which is generated may not be adequate. And if it is a heat exchanger sort of thing, then you may require a like this. This is a thermosiphon system. Okay. This is, if it is a large system, then you may require a pump, which you say a post flow sort of thing or an active system. And then it may have an auxiliary also. It may also have a, means if you make a closed loop sort of thing and can have a heat exchanger here, which can be tube in tank or tube in tube type of heat exchanger. Means if you have the double wall type of tube in which the inside the tube, the same water is or the same liquid is flowing continuously through these collectors and outside the water which is being used, then that is basically tube in tube type of thing. Or you can have a tube in tank, means you have a tank, hot water tank, inside the closed loop type of heat exchanger. In that case, you say tube and tank type of. Like swimming pool sort of thing. You see, a lot of collectors are there which are unglazed, and the water is circulated through pump, and which is coming to this pool, and you get a reasonably that type of application means you don't require a glazing because ultimately because you don't require a very high temperature. Okay. And what I was mentioning about the power generation. So it is an absorber tube. The solar radiation is falling here and then from multiple things because it is a parabolic trough. So a lot of means in this point from multiple points, the solar radiation ray is falling, and that's why the temperature of this is maybe very high. And then this is a dish type of collector where this is I say it line collector, line focusing collector. The parabolic trough is line focusing collector. You see, in a line, the collection is taking. And this is the point focusing collector. It's a paraboloid basically. And in this point, you get number of radiations which are falling. So the temperature at this point may be 300, 400, 500, even 800 degrees Celsius. Here I am using the Fresnel lens. Means from different point I am giving solar rays to fall at a particular point. So the temperature may be very high. And I put such material, such liquid here. The temperature then water then commit the boiler. So for this in Turkey, perhaps one such type of power plant is there. In Solar Center also, I'm habitual of talking there is a center. It's a National Institute of Solar Energy now. You can see all those systems. You can visit there and see all these systems working. Of course, mainly for this is basically the solar pond, which, as I mentioned, that there are different uh, temperature ranges, which are because of the different concentration of the shoddy water, and ultimately at the bottom, the heat is collected, and then the cool water is going and the hot water is coming out from here. So that's how the solar pond system works. This is in the same principle is being used for space heating purpose. I have already shown it. Then there are the passive building concept, which is coming, wherein you design a building in such a way that a particular uh, you can gain maximum heat inside, and make the sometimes that is one imitation place within India now, that having large building being a lot such, and actually, as I mentioned, that glass has a tendency that it allows the lower wavelength to go inside and the higher wavelength it's opaque. So the temperature inside gets heated, use more air conditioning and all that. So that's not a good way of doing the thing. Yes, in the western part, that where the temperature is low, is okay, but in India, perhaps that is not good. But that's not okay. Making the passive building comfortable. Some experiments were done. One is there in Lucknow, NIDA guest house that's made with the passive concept. Even the original building of National Institute of Solar Energy was also based on solar passive concept, wherein we have used almost all concepts which could be possible, demonstrated there, the older building, not the newer one. So that's what, friends, I had to share. I think I could give some insight. Of course, I'm not very good in mathematics and all that, and perhaps to some extent away from calculations. Uh, give you how work can use the floor is open now.
Hey, thank you very much, sir, for your elaborative and descriptive talk about solar thermal system. Now I request the participants, if you have any query regarding sir solar thermal systems or what presentations we have made, you can ask to sir. Okay. Any questions from the participant and the dignitaries to sir? You can ask your query. He is available to answer your query.
And I would love to see the faces also if possible.
Okay. Any participant who want to ask any questions to sir, you can ask. You can ask your queries. And sir want to with your video, so you can switch on your video and ask the question.
Yeah, otherwise also, if not on solar thermal system, then ask question on general aspect also. It's not.
You
Good evening, sir.
Yeah.
Hello, Pradeep sir. Namaskar.
Ha, namaskar, namaskar.
Sir,
Can
actually,
you, please introduce yourself.
pardon?
Please introduce yourself first.
Sir, myself Harish Khyani from Jodhpur, Rajasthan.
हाँ बताइए हरीश जी.
हाँ. Sir, मैं research scholar हूँ.
Mhm.
Sir, actually, in case of conversion of solar energy into electricity, we have two paths. One is direct and other is indirect, right? In case of solar photovoltaic, although you have discussed about the thermal, but I want to ask the question on solar photovoltaic.
Yeah, no problem.
Sir, in case of solar photovoltaic, we don't need much temperature because the efficiency will come down as the temperature increases,
Mhm.
right?
Mhm.
And
Yes.
our photovoltaic panels are basically rated at maximum power they will give on 25 degrees centigrade. If the temperature will increase, then their performance will deteriorate. So how can we maintain this temperature? Is it possible?
First and foremost thing, if you have noticed, what I said actually, that in the solar thermal system, it's the heat portion basically which we use. In the photovoltaic, what I had mentioned was the spectrum portion. It's not the heat aspect, but it's the intensity of the solar radiation, number one, that plays, and then the temperature. As you rightly mentioned, the temperature plays a very important role in photovoltaics. As the temperature rises, the efficiency goes down. Practically, one thing is it's not the temperature of the atmosphere, but the temperature of the cell. Okay, it is the as per the standard process or the standards which have been made. See what is happening. Now look at see why we say 25 degrees Celsius. First, we have to understand this. Okay, for any system actually, particularly the solar energy, the solar radiation acts as fuel. Okay, as that full supply is there, you will have energy. It may be heat, thermal, or it may be electricity, photovoltaic generation. Okay, now look at the morning time. Your solar radiation level is quite low. As the day increases, the solar radiation level increases. So the generation level, maybe if you have a 100-watt module or say 300-watt module or the 500-watt solar module, at the morning hour, maybe at 8 o'clock, and if the radiation is very good, maybe sometimes in September or October, you are getting around say 900 or 1000 watt per meter square. So at 8 a.m., the generation from a say 100-watt module, I'm using the 100-watt for calculation purpose, the generation will not be 100-watt, but the generation will be hardly 20 watt or 30 watt. As the day increases, and at 12 o'clock or 1 o'clock, that 100-watt may generate 100 watt, that 100 watt may generate 95 or 90 watt, whatever it is. Okay, that is one aspect. So the change in radiation means because the solar radiation is not falling normal to the surface. Okay, and that's why the part of the radiation will get deflected. So you are not getting the maximum output of it, but you are paying for 100 watt. So at what condition the 100 watt should come? And that's why I never use 100 watt. I always use 100 watt peak. So peak is the standard which we have set. The standard is that the radiation level should be 1000 watt per meter square. The spectrum of the radiation, that's why I'm using the word spectrum, should be air mass 1.5. I had explained actually the air mass also. The air mass 1.5 and the cell temperature should be 25 degrees Celsius. Now, this is the entire thing. Now, what has happened? Why the temperature is rising now? The cell temperature is normally at a thumb rule, you can say, it's not absolute. To some extent, it's 23 degrees higher than the ambient temperature. So the cell temperature, because the radiation, whatever is falling on the solar cell or the module, the entire radiation is not absorbed. The heat radiation that will means the part of it, which is the heat radiation, that will get absorbed and that is the temperature. Higher wavelength from the whatever is the band gap of that solar cell, the higher energy of the band, what it will do? It will electron from the west band to go above the conduction band and from come to the conduction line.
Sir, your voice is not coming clearly.
So again, that will also increase temperature. So that I can't do anything yet. I'm trying to put the mic on my. So what I mean to say, there are different processes which are going on inside that, and that's why lower the temperature, higher will be the efficiency. So the 25 degree is an standard. It is not sacrosanct sort of thing, and that's why sometimes we also use the word NOCT, normal operating temperature, that, and we also make characterize the solar cell at NOCT, normal operating cell temperature. So this is the thing. So we have to understand in photovoltaic. And now what you said that how you can use. Now there are researches which are going on where you use in place of only photovoltaic system, you use the photovoltaic thermal system. So you, because now the cell temperature has gone higher. If the cell temperature has gone higher, then if somehow you can make it as a collector, now it has become collector because the temperature is higher. So you can transfer that energy to a working flow and then use that working flow for any other purpose. Just like in a solar thermal device, I explained, then perhaps you will get optimal, you can have optimal utilization of that. Part of that work was done at IIT Delhi also. At some point of time, Professor G.N. Tiwari had also worked on that. Professor H.P. Garg had also done some work on that. But so far that process is not effectively commercialized. But yes, people have been working in that direction also, so that you can maintain the temperature at a lower level. And The physics of the temperature rise. That's the, as I mentioned, the ambient and more than the 20 degree higher than the ambient temperature. So if the ambient temperature is 40 degrees Celsius, the cell temperature will be 63 degrees Celsius. And what you have been mentioning is the 25 degrees Celsius. That is the at which the cell is irritated. So naturally the efficiency will go down in real operating temperature. Okay. So if you can transfer part of that energy heat to a working fluid, you can reduce that. That's what it is at the moment.
Okay, sir. Okay, thank you.
Hello, sir. Hello, sir.
Yes, please.
Am I audible, sir?
Yes. You please introduce yourself.
Yeah. So my name is Jishnu. I am a research scholar from Kerala. Sir, my question is, sir, you have told that usually in solar thermal collectors, the more we optimize the system, the higher temperature we are able to achieve at the absorber position, right, sir? Like we could concentrate more heat towards the absorber and we could achieve a higher temperature. So, sir, usually we employ like this higher temperature is mostly used to generate steam to convert this into energy, some form of energy. Sir, I just want to know that how far have we gone forward with the use of some advanced devices like heat pipes, which could actually transfer the heat much faster from a high temperature point. Again,
See,
sir.
Yes.
Yes, sir. Sir, one more associate. Yes, sir. One more associated question is that, sir, are we anywhere using a thermocouple which uses the Seebeck effect so that this high temperature achieved at a particular point in the absorber can be used to generate EMF and convert to energy?
See, practically your second question, perhaps I am not the good person to answer, even for the first question also.
Okay.
But yes, as far as the heat pipe and all those things are concerned, they are already being in use.
Okay.
Particularly in maybe wherever we want to use it, maybe in a Stirling engine or maybe in refrigeration and the cooling type of air conditioning application sort of thing.
Okay, sir.
We are using those type of thing. But see what all has happened. Unfortunately, the solar thermal in
Yes, sir.
India, when you have to concentrate, okay.
Yes, sir.
For concentration, you require a good direct normal incident. The beam radiation, what I mentioned,
Yes, sir.
that can only be concentrated. As far as diffuse part is concerned, it's a diffused only, so you cannot concentrate. It's
Yes, sir.
the direct beam radiation only. But in India,
Yes.
you normally see the DNI level is not very good. Okay, so
Okay.
that's why the solar thermal power generation per se, we started with means way back in late 80s, 50 kilowatt solar thermal power plant was set up in of course, a lot of experiences were gained through that solar power plant, but that could not be scaled up. There is only one power plant which was by Acme, so through thermal, but practically that we do not DNI because whatever it is, unlike in where got a bit much work is not being done. That's why later.
Okay, sir.
Any more questions? Queries you want to ask, you can ask. His presence is still available with us. So whatever queries you want to ask all the participants under the disease, you can ask, sir.
See, as far as asking question is concerned, see, the questions are not stupid. Answers could be stupid. So don't hesitate in asking questions. Okay.
No, sir.
And if I would be able to answer that question, it's good. If I would not be, at least it will give me a food for more learning. That's how we learn. Okay. So I would encourage actually all the participants to come forward. The questions are never stupid, because most of the time actually we avoid asking a very basic question. And sometimes it happens that a very learned person cannot answer a basic question. So it doesn't mean that he doesn't know it. It's basically at that particular moment he is not able to answer that. That's what it happens in interviews also. You know the answer, but you cannot answer at that time. So it hardly matters. So you raise question, no problem. And raise question not only on solar thermal, maybe some other aspects also, because it's I'd worked for about say 30, 36, 38 years if the reserve period is also added. So maybe some of the fields also.
Any questions, queries you want? Sir has asked that you can ask questions from other fields also related to renewable energy. He has a vast experience in the field of renewable energy, so you can answer, ask your queries or questions, whatever you have. Sir is available with us. His presence is esteemed for us. Please ask any queries if the participants want to do so.
It seems either which is better option to generate electricity. That's one question in the chat box. What was the question? Thank you. Very informative. Very informative. Can you repeat? Not. Which is better than the Hemant Deshpande, which is better option electricity, using solar thermal energy or using solar PV technology. See, practically, as I mentioned, efficiency, if you look at perhaps the thermal option is a better option. Okay, but as I mentioned, in India, particularly because of the limitation of not having a good DNI, this aspect is not being pursued much. But there are places where solar thermal power generation is being given priority, particularly in some of the countries and as I mentioned, Turkey and all those places. Okay, but yes, financial viability is still a question in the solar thermal application. But as far as efficiency is concerned, definitely the thermal is better than the PV. But the PV route, lenient route. In fact, the thermal power generation practically initial part where you get the heat and then transfer that heat to a working fluid and then put it in a boiler. After that, it's a normal thermal power product. Okay, so whatever infrastructure infrastructure is required for I think I have given a very good lecture. And everything is nothing is understood by the participant because there are hardly any questions which are coming up. Hello. Hello. Not getting. I'm not getting any voice. So now I think let me give it to the host because I don't see any reactions coming from the participants. So they might have got busy actually. Yeah.
First,
Yes, yeah, I'm not getting any voice actually from the host side. It's a
thank you very
can you use the chat box actually if I think I myself should close it here itself. Appears to be because I'm not in a position to hear anything from anybody. So if no question, then thank you very much. It was nice talking to you, and of course, very little interaction, but whatever it is, and my contact details are already there in my presentation. I think they will. It is already available with you, and you can contact me for anything. Okay. So thank you. Thanks a lot. Okay. So I'm now closing from my side.
Hello, am I audible to the participants? Are the participants able to hear me?
Yes, sir, you are audible.
So sir is actually did not find any queries and he has left us, Pradeep sir. Now we will get in touch with at 2:30 p.m. Till then you can take a break. As at 2:30 p.m. we have a very efficient lecture on thermal energy storage systems by one of our esteemed and privileged speakers, Dr. Atul Sharma. He is quite a big name in thermal energy storage. So please be patient, take a break and be with us at around 2:30 p.m. for his lecture. Till then you can take a break and thank you for your cooperation and support all the dignitaries and the participants. Will get in touch with us at 2:30 p.m. for lecture on Dr. Atul Sharma. Thank you. Thank you.